So today's class, we're going to look into SPARQL 1.1 specifically, and we're going to conclude the part of the course on the SPARQL query language. So we'll speak about the new features in SPARQL 1.1 and what kinds of queries they enable. So previously, we spoke about SPARQL, okay, but we had focused primarily on SPARQL 1.0. So SPARQL 1.0 was recommended in 2008. And since then, there's this new version, SPARQL 1.1, that has been released. So we're going to focus today on this new version, which was published, recommended by the W3C, the World Wide Web Consortium, a standards body for the web, which was, and they recommended in 2013, the extended version of SPARQL called SPARQL 1.1. So we can have a look at the new features that were included. So the goal of SPARQL 1.1 was to extend SPARQL with the most important features that people felt would be useful. So the first feature that was added was negation. So we mentioned in the last class that SPARQL 1.0 is negation is possible in SPARQL 1.0 with this trick, where we use optional to find if something is available, and then we use a filter not bound to verify that it's not available. Okay, so this will return a date if it's available, and then this filter such that in all of the solutions, date is not available. So this is a form of negation. So this is a bit messy and a bit weird. So in SPARQL 1.1, which maybe some of you found as well while doing the previous lab, there are two explicit forms of negation. One is filter not exists, where essentially this query asks for give me movies such that there does not exist a first air date for the movie. Okay, so this is a negation similar to except in SQL. So the solutions for this would be Sharknado 2, because Sharknado 2 does not have a first air date. On the other hand, we don't get Sharknado as a result, even though it is of type movie, because it has a first air date. Okay, so this is all of the movies such that they do not have a first air date. There is a second form of negation called minus. And minus essentially has a very similar meaning. So it does pretty much the same thing. In this case, it finds us movies that do not have a first aired date, which will again return as Sharknado 2. So we have these two different forms of negation with some subtle differences between them. What is the difference between minus and not exists? We have a flower here. This part is green. Maybe one more. Symbol on the hat is different. I think there's a couple more you can look for later. So it's hard to spot the differences. So not exists returns solutions if the pattern on the right has no matches when replacing variables from the left. So if we have some solution from the left and we replace the variables for that solution on the right, then we want to check if there does not exist something. In fact, it was later realized after publishing the SPARQL 1.1 standard that this is not well defined. There are cases where you can't just replace variables because you create something that's not a valid query. So not exists is sort of, and it's not really been fixed. So there's actually some ambiguity around what this actually means. On the other hand, minus removes solutions from the left that join on the right, where there's at least one variable in common between both solutions. So, okay, what does that mean in practice? What's the difference between these? So if we take one solution here, which is a slightly, or we take one query here, which is a slightly strange query. In this case, we're asking for movies such that there does not exist a series. We're using this for filter not exists, and we're using it for minus. The slightly strange thing here is that there's no variable in common between the left of the filter not exists and the right. Yeah, so we see that actually these use different variables. So on the left-hand side, we'll get empty results. Why is that? because no matter what movie we have here, there does exist a series. So essentially we filter them because it's filter not exists. So there exists a series, which is Sharknado series. So this is enough to remove all of the results here. On the other hand, with minus, since there isn't at least one variable in common, this solution here is ignored. So there is a match here, so therefore no results. And in this case, since there's no variable in common between the left and the right, the minus is effectively ignored. And we return all of the movies, which are Sharknado and Sharknado 2. So this is maybe one of the more problematic aspects of the standard, in that the way negation is defined is not the cleanest, in my opinion. It's not a big deal, I think, because these queries are a bit strange anyways, but yeah, so there's some subtle differences between minus and filter not exist, but in general, they're quite similar features. Okay, any questions or doubts? Okay, so let me find something here. Here it is. So, okay, this feature is quite interesting. This feature is quite cool and something different from SQL, or different from other query languages to a certain extent. There are other query languages where we can search for paths, like XPath, for example. But property paths are a characteristic feature of graph databases. Some graph databases, if you have seen Neo4j, they only support some types of expressions. SPARQL has a fairly long list of expressions that we can use. And the idea is to specify an expression that will match arbitrary length paths in the graph. So it will allow us to find paths in the graph that match the regular expression that we specify. So we can specify a path using simply a label on an edge, which is a predicate. This is essentially what we've seen before. We've used this a lot, so there's nothing special about this. We can also use the syntax for inverse paths. We can have something followed by something else. For example, father followed by mother. We can have a path of E1 or E2, for example, brother or sister. We can have a path of 0 or more E. So for example, for ancestors, parent star would get us ourselves and our parents and our grandparents and so forth. Path of 1 or more E. For example, if we had parent plus, then we would get our parents or grandparents and so forth, but not ourselves. E question mark is a path of 0 or 1E. So this would get us ourselves or our parents if we had parent question mark. Any predicate not P. So for example, if we had not cousin, then we would get all of the things connected to the nodes that are not cousins. We can give a list of nots. So we can say not P1 or P2 or P3 or PK, and not inverse PK plus 1 to PN. So we can give a list of all of the predicates that we're not interested in. And we can also use brackets for grouping. So we can say, for example, mother or father star in brackets star, which would be essentially all the maternal and paternal ancestors. So with this, we can express new types of queries that are really quite useful in the context of graphs. So these features here are the only ones that really enable something new. Everything else we could rewrite, for example, by using union, or by doing a join, or by simply reversing the subject and object variables to search in the other direction. So everything else we can, to a certain extent, or we can express without using property paths. But this here allows us to express transitivity and to search for arbitrary length paths. So an example of how we could use this is if we have an RDF list, as we saw in class 2 on RDF. Here we have Sharknado series, and we represent a list by pointing movies to essentially the first element of a list, and then every element of the list points recursively to the rest of the list, as well as to the element of that part of the list. So this says that Sharknado series has the first movie, Sharknado, second movie, Sharknado 2, and third movie, Sharknado 3. Note again that we use the property first in every case because it's the first element of that part of the sublist. Okay, but with respect to the head of the list, this is the second element and this is the third element. So which movies are in the Sharknado series? How can we query for this using property paths? We can use the following query here, which says, okay, starting from Sharknado series, follow one movie's edge, okay? And then follow 0 or more rest, okay? So, and then follow first. So we first go to movies and then we go 0 or more rest, which will bring us here, the node itself, or here, or here. And then it says go 1 first. So from here, we'll go to first, from here to first, here to first. And we get Sharknado, Sharknado 2, and Sharknado 3 as a result. Okay, so 1 movies, 0 or more rest, which will bring us to here, here, or here. And then from there, advance 1 first, which will bring us to here, here, or here. Okay. So we get Sharknado, Sharknado 2, and Sharknado 3 as results. So here it's notable that we don't return the paths themselves, but rather just we can return the endpoints of the path, the start nodes or the end nodes or the pairs that are connected by those paths, but we don't return the paths themselves. As another example, we can find people with a finite Bacon number. So here we have Kevin Bacon. And the finite Bacon number essentially, or a Bacon number is how far away you are in this co-acting graph from Kevin Bacon. So Tim Robbins in this case would be a distance of, would have a Kevin Bacon number of 1. Megan Ryan would have a Kevin Bacon number of at most 2. Maybe she directly acted with Kevin Bacon in another movie, but at most 2, and Nicolas Cage at most 3. So what we want to find essentially are, in this case, people who are connected to Kevin Bacon through a co-acting relationship. So how do we do this? We can again use a more complex property path here. So what we need to do to find these people is we need to start from Kevin Bacon, okay, which we specify here. And then we need to traverse in the inverse direction of actor. We need to go backwards across actor because we need to go against the edge direction. So we're going to go inverse actor. And then we need to go forward. So then we need to go forward actor. Okay. So inverse actor followed by inverse actor. However, there is a complication in that we have the actress relation here as well. So really, when we go back and forward, we should check to make sure that we're going back or forward actor or actress, which we can also do with a property path. So what we have here is Kevin Bacon, and then we have go back an actor or an actress. So we're going to go back to the movie, okay? And then we're going to follow that by going forward from actor or actress. So from the movie, we go forward to actor or actress. And we do this 0 or many times, right? So essentially one path would be from Kevin Bacon, we go backwards to the movie, and we go forwards again to Kevin Bacon, or we can go Kevin Bacon, actor, back to the movie, forward to the actor, Tim Robbins, Kevin Bacon, Tim Robbins, Top Gun, Meg Ryan, and so forth, and Nicolas Cage as well. So we can do this reverse actor or actress, forward actor or actress, 0 or many times to find all of the people connected to Kevin Bacon recursively in the graph. And these are the solutions. So we get Kevin Bacon because it's 0 or many. So we just return Kevin Bacon immediately, as well as the fact that we could go back and then forward in the same way to Kevin Bacon, Tim Robbins, Meg Ryan, and Nicolas Cage. We also get a set of results. So we don't get Kevin Bacon twice, even though there's multiple paths that lead to Kevin Bacon. We could go, for example, Kevin Bacon, Mystic River, Tim Robbins, Mystic River, Kevin Bacon, right? So essentially that would obviously start to lead to an infinite number of paths, because we could go Kevin Bacon, Mystic River, Tim Robbins, Top Gun, Tim Robbins, Top Gun, Tim Robbins, Top Gun, Tim Robbins, Mystic River, Kevin Bacon, an arbitrary number of times. So we solve that problem by returning a set of solutions, just the nodes that are connected by the paths. We know that must be finite because there's a finite number of nodes in the RDF graph. So we can get at most n squared results here. Note that we cannot get the actual Bacon number. We can't get the distance in SPARQL. We could for a finite length. So we could check, paths like this of length 2 or length 3 or length 4 simply using joins, but we wouldn't be able to do this for an arbitrary length path. Any questions or doubts about this? Okay, so what we have here are effectively regular expressions. So we can express or capture interesting paths using this feature. Okay, so that's probably, I would say, one of the most important and interesting features of SPARQL 1.1. But there are a number of very useful features aside from paths. However, they're perhaps similar in a way to what we would see in SQL. So the first thing would be assignment with bind. So maybe, for example, in our query, we'd like to not return directly some value from the graph, but we would rather like to compute a value and return that. So in this case, for example, maybe instead of returning the date, we only want to return the year 2013. So in this case, we're doing precisely that. We're getting the first air date of the movie, and then we're extracting a substring of the date, and we're taking the substring from 1 to 4 and converting it to an int and returning that as the year. So for every movie, we get a number that represents the year effectively in this solution. So we get Sharknado in 2013. So bind allows us to compute a value using an expression like we saw in the previous class, and to return that or to fix that to a variable. We can also specify if we want, maybe we have a bunch of different alternatives we want to search for. We have maybe already a list of results that we're interested in, maybe a list of 10 movies we're interested in, and we want to do queries with respect to those. We can insert a table of solutions into the query using values. So what we do here is we say values and the variables that we would like to bind. And then we can specify solutions tuples that correspond to those variables. So undef here means essentially that it's undefined or unbound in that solution. So what we're doing here is defining two solutions. One where the movie is undefined, which means it will join with anything, and the other where the star is Tara Reid. And the second one where we have Sharknado 2 is the movie and the star is undefined. And then we're asking for movie stars star. Okay, so taking the first solution here in values, movie will be undefined. So what we'll be searching for will be movie stars star, which will be movie stars Tara Reid. So we're looking for what movie Tara Reid stars in, which is Sharknado. And then we have Sharknado 2 stars star, where star is left undefined, so it's still a variable. So we're looking for inzering here. And our results will look like this. So we'll have both the movies that Tara Reid has starred in, as well as the stars of Sharknado 2. Okay, so this is two forms of assignment of assigning values to variables in the query. We see that there's no result for Sharknado inzering here. Here's this triple here. So the where matches that, but Sharknado does not. Sharknado matches here, but this will not match with the inzering. And inzering will match here, but this won't match with Sharknado. So this result is filtered. We're not interested in that result. Any questions or doubts? Okay. If not, then we could speak of aggregates, which are very similar to what we would see in SQL, queries with group by effectively. So let's say, for example, we wanted to know how many movie stars are in the data. So how many people are starring in movies here? So we could see 1, 2, effectively, intuitively speaking. So how could we actually query for that over the graph? Well, we can write a query as such, where we have movie star, and then we're just counting how many results there are for the star variable specifically. So count star is count. So how many solutions would we expect here? Anyone want to guess? So we might be expecting 2, right? Because if we look here, we say 2, but we'll actually get 3. So why do we get 3? It's similar to SQL as well. We get 3 because there's actually 3 solutions in which there is a star. So we get tire rate here, we get 1, we get 2 for Ian Ziering for Sharknado, but we get a second one for Ian Ziering for being in Sharknado 2 as well. So since there are 3 base solutions, we will get a count of 3. Okay. So if we wanted to have a count of 2, if we wanted to provide a distinct count, we could select distinct count star as count, which in this case would return as a result of 3 still. Okay, so why do we get 3 and not 2, even though we have distinct? Well, if we put distinct here, it's the default distinct, which is getting rid of duplicate results. But there is no duplicate results. There's just one solution that says 3. So what this means is that, well, we haven't really solved the problem, right? This distinct outside doesn't really help us because this removes duplicate solutions and there's no duplicate solutions. So distinct will be applied after count in this stage. So if we want to do a count of distinct elements, we put the distinct inside the count brackets. Count distinct star is count. And this time it will return us 3 again. No, it will return us 2. So we get 2 this time. Okay. This is count. It's similar, same thing happens in SQL and in other query languages as well. How many stars does each movie have? So this involves not just a global count, but it's a count per something. In this case, it's a count per movie. So we want to return Sharknado as 2 stars and Sharknado 2 has 1 star in the graph. So in this case, we can apply group by as we would in SQL. And then we can return the group by variables or any subset of the variables that we put in the group by. And we can then apply an aggregation over the other variables that are not grouped. So in this case, we're going to group by movie, and then we're going to select movie and count distinct star as count, which will return as Sharknado 2, and Sharknado 2 having a count of 1. Okay, and we can group by multiple variables here, much like in SQL. That's no problem. So how about give me movies with more than 1 star? So what we want to do is the same query, but we want to filter Sharknado 2 because it only has 1 star. Does anyone remember how to do this in SQL? What's the neatest way? So there's a couple of ways we could do this. There's one feature particularly for this sort of query in SQL. And it's called having. So it's like a filter, but for aggregates. So what we can do is the exact same query as before to get the number of stars per movie. And then we can add at the end this having count distinct star greater than 1. So it allows us to specify a filter outside the query to a certain extent, outside the rest of the query. And essentially we'll apply this filter after applying the aggregation, right? We can't add a filter here because a filter here doesn't have access to the count. A filter has to go inside the where clause, and there's no count available in the where. It's selected or it's computed outside the where clause. So having is like a filter just for the final results, right? And it allows us to apply aggregations, to apply conditions over the aggregations. So in this case, we'll return 2 solutions. There is another option, which we'll see in a moment, which is to use a subquery. So we can create this query and then in an outer query, use filter, with, which we'll see in a little while. But this is much cleaner and possible, if possible, to use this, where it's possible to use this. Okay, so having is like a filter for aggregates. What are the functions we can apply in SPARQL 1.1, the aggregate functions? We can apply count, sum, min, max, average, group concat, which allows us to concatenate all of the values in a group. For example, if we wanted to, oh, so for example, if we wanted to list all of the stars of a movie, we could use a group concat. And sample, which allows us to return some value. So if we wanted for every movie to get 1 star, but we didn't really care which one, we could use sample to select a value, a star of a movie pseudo-randomly. Okay, so one more aggregate to take an example that's not count. We can take sample. So here, for every movie, we're doing the same thing. Here, we're actually applying a different halving condition to the actual aggregation we apply in the select. So we're still looking for movies with more than 1 star, and then we're going to sample randomly a star for that movie instead of counting them. So in this case, we'll have Sharknado, as it's the only movie with more than 1 star. And then we're going to randomly select one of the stars. So we'll select, in this case, Tara Reid. Or we could select Inzuri, right? So either one of these would be a valid solution. Okay. So in general, aggregation is very similar to SQL. So any questions or doubts about that? No doubts? Okay, so talking about counting things and saying how many stars does a movie have, for example, we might start to think about the class and owl, where we were like very careful. We were saying, you know, in this case, if we look at these data, how many movies does Sharknado have? Well, according to OWL, how many stars does the movie have? According to OWL, it would be at least 1, because we don't know that Tara Reid and Inzuri are different, right? Or we also don't know, for example, if there are more stars, because the data might be incomplete. So we're very careful. In the case of well, the example we saw at the time was how many children does Vito have in this example? And we had said at least 1 child, right? So it's the same thing here. If we apply the same logic for how many stars does a movie have, the movies here would have at least 1 movie. However, in SPARQL, if we apply this query over this graph with 1, 2, 3, 4 triples, Vito has child Connie, Vito has child Sonny, Vito has child Fredo, Vito has child Michael, and then we ask how many children does Vito have, the solutions we'll get will be 4, not at least 1, right? So you might think, well, this means that somehow SPARQL is contradicts or has different semantics to OWL. But in fact, what's going on here is not the case. So essentially, you might think, okay, well, maybe SPARQL assumes that every term refers to something unique, has a unique name assumption, and also has a closed world assumption, meaning that we know or assume that there's no other facts. So if it's not stated that Vito has another child, then it's false, effectively, that Vito has another child. If it's not stated or implied. However, that's not the case. Essentially, what's happening is that SPARQL does not interpret. It doesn't have worlds. It doesn't interpret real people. It doesn't try to do that, right? What SPARQL is doing is it's working on data. So it's counting. In this case, the clearest explanation is that SPARQL is counting RDF terms. It's counting how many terms there are. It shouldn't be interpreted as counting how many children Vito has. Really, it's just counting how many objects in the RDF graph have the subject, have a triple where the subject is Vito and the predicate is has child. It's not in any way kind of counting how many children Vito has in the real world. Of course, in some cases, there's going to be a correspondence between both results, right? but not always. In this case, we're really just counting how many values are here for Vito has for child. I've not checked the time in the, okay, so we're just at the time for a break. Any questions or doubts about this? Okay, so there's quite some debate in the community about this, but this is how I view it, that SPARQL is just counting RDF terms, and therefore it doesn't contradict OWL. It's just a different level of at which we're operating. So we'll take a break until 10:55, I guess, 10:56 maybe. And I'll post the post activa in a minute once I find it. So see you in 10 minutes. Okay, so as we spoke about when we're counting in SPARQL, we're really just counting terms in the RDF graph. We're not really counting people or children here, which is sufficient for many applications. That makes life a lot simpler. But it's different to what we've seen with Rdfs and with OWL in particular. So another feature we have in SPARQL 1.1, that's new to SPARQL 1.1, is the ability to express subqueries. So for example, if we wanted to ask how many stars does a movie have on average? So we wanted to count how many stars each movie has and then take the average across all movies. In this case, we would expect 1.5 in that we have 2 for Sharknado and 1 for Sharknado 2. So how do we express this query? Well, we have average in the aggregation, in the list of possible aggregations we can apply. The problem is that we need to count first and then apply an average. So really what we need to do here is we need to use a subquery because we have a sort of nested aggregation here. So we first count how many movies there are, how many stars there are per movie using a query similar to what we saw before. And then in the outer query, we're going to take the average of those counts as our final solution, which will be 1.5. So in this case, we need to apply an aggregation on top of an aggregation. So we can use a subquery for that. So subqueries are useful when you need solution modifiers or aggregates in the middle of a more complex query. So the most common case is this sort of nested aggregation case. So yeah, we can express this in SPARQL 1.1, similar again to SQL. Which movies have more stars than average? So in this case, we'd expect Sharknado 2. It has 2 stars, which is greater than the average 1.5. So in this case, it's a similar query. We start by counting how many movies there are or how many stars there are per movie. We take the average. And then outside, okay, again, we need to find how many stars a movie has. And then we apply a halving. So we say that the count of the number of stars must be greater than the average. There's one thing to note here, which is that here we add average to the group by. And this is so that we can access the average outside as part of the group. Since there's only one value for average, it doesn't actually change the grouping, but it allows us to access the average outside after we apply the grouping. So it allows us to apply this, this halving here based on average. And then we return the movie. So in this case, we have Sharknado. So in this case, we have 3 levels of select, right? We have the inner select to count how many stars per movie, the middle select to count to compute the average number of stars per movie, and then the outer select to find the movies with more than average stars. Okay, so one thing to note here is that movie here does not correspond with movie here. So essentially, once we apply this select, once we apply this select here, we forget about, in some sense, all of the other variables that were mentioned inside. So this movie here has nothing to do with this movie here. In fact, we could rename this variable movie here to whatever other variable we might like. We could call it M, and the query would be exactly the same, right? So there's no relation between these, or they do not correlate. So what we do essentially, what we can think of here is that we evaluate the inner query first and send its solutions outside. And then we evaluate this query and we send its solutions outside, right? So it's sort of starting from the innermost queries, evaluate them, and then push their results outside. There's no relation in that sense then between movie and movie, because the results here do not speak about the movie variable at all. They only return a count. Okay. Any questions or doubts? Okay, so a cool feature for SPARQL, given that we're working on the web, is federation. And what federation allows us to do is effectively it allows us to query other endpoints that are on the web. So as we mentioned previously, the endpoints, SPARQL endpoints, are often made public on the web. They're made available online, so users can write whatever queries they might like to answer. And we already spoke about the Wikidata Query service, where you can write some cool queries and get answers back. So what federation allows us to do is to execute a subquery remotely. So it allows us to call a different SPARQL endpoint on the web in order to get some results. So here we have a real example, which is, okay, a little bit complex perhaps, but what we're looking for is embassies in Santiago that are embassies of Asian countries. The problem is that we don't have all the information we need in Wikidata. We don't actually have all of the coordinates of the embassies. However, there is this external data set called linked geodata, and in linked geodata, we have precisely this information. So we have information about embassies and we have their geo coordinates. So, however, in linked geodata, we can find the country of the embassy, like a code for the country of the embassy, like CL, but we can't say whether or not it's in Asia, but we have that data in Wikidata, right? So we have part of the data we need in Wikidata and part of the data we need in linked geodata. So in this sort of case, what we can do is we can run this federated query, which will which will find the embassies on linked geodata, and based on their country code, we'll check in Wikidata that they're actually in the Asian continent. So I think we can try to run this. I'm going to stop share screen. I have it already loaded here. So here's the query in the Wikidata Query service, which has this local part here that will be run over Wikidata. And then it has this part here, which is the federated call. So if we run this query, what we're expecting again is to get a map where we have the points referring to Asian embassies in Santiago. So here we see the points that we found. Let me see if I can, I'll just zoom down here, it's fine. So what results did we find? We found the Turkish embassy, Korean embassy, Vietnamese, Indian, Iraq, Syrian, Israeli, and the Russian embassy. So yeah, this involves results that come from two different endpoints that we're matching. So we can apply this in general to other examples. We could even have queries that involve 3 or 4 or 5 endpoints. One of the challenges of this is just that how to do the joins. So we need some way to do the joins. And this is a kind of a nice example because we have country codes in both. It's quite unlikely that we're going to have the same identifier sets in both. However, Wikidata does provide a lot of links to different data sets. For example, for movies, we have 20 different types of identifiers like IMDb, Rotten Tomatoes, Metacritic, these sorts of things. So we can use these to enable federated queries. So this is a very webby, semantic webby, web of data sort of feature. We can invoke SPARQL features and SPARQL endpoints and elsewhere on the web. So this finds Asian embassies within 10 kilometers of Santiago Center. The embassies are taken from linked geodata and the continents are taken from Wikidata. And again, we could combine multiple different services here to query, combine results from 3 or 4 different SPARQL endpoints on the web. Any questions or doubts? Okay. So like in SQL, we have a language that allows us not only to query data, but to also manipulate the data, by which I mean we can insert data, remove data, create tables, and so forth. In SPARQL 1.1, there is a new language called SPARQL 1.1 Update, which also allows us to modify the graph, to modify the named graphs and the default graph indexed in the underlying data set. So the simplest case is we can just insert some data. So we can say Sharknado series, third movie, Sharknado 3. And if we insert data without specifying that graph, we'll insert it into the default graph as we see here. If we want to insert data like a triple or multiple triples into a specific named graph, all we have to do is use the graph keyword, give the name of the graph, and then the triples we want to insert into it. And this will allow us, for example, to add this new triple here, Sharknado 2, first air, 2014, 0730. So we can insert data into that default graph or into named graphs. We can also delete data, so we can remove specific triples from graphs. So in this case, we're going to remove Sharknado series, third movie, Sharknado 3 from the default graph. We could also remove data from a named graph by specifying the keyword graph, the name of the graph we want to remove the triple or triples from, and then specify here the triples that we want to remove. So we use delete data in the case that we're specifying the entire triples. What about using queries to manipulate the data? So we can do that with a where clause, combining, for example, insert or delete with where. So what we can do in the where clause is we can query for example, we can find the graph associated with the second movie of the Sharknado series, and we can query for all of the triples about that, right? So then in the insert, we can use the results of the where clause to specify what we want to insert. So essentially what we're doing here is for the same graph or graphs returned here, for the movies returned here, we're going to insert that this is the second Sharknado movie. Okay. So it allows us to use some variables in the insert that will be replaced by the results from the where clause to specify possibly multiple insertions of data. We can do the same for delete. So for example, in this case here, we're looking for the first movie of the Sharknado series, and then we're looking for the graph that gives the title of that movie. And then we're going to delete from that graph the title of the movie. So we're going to essentially remove all of the titles of the first movie of the Sharknado series from the respective name graph. We can also combine insert and delete. So we can specify our where clause here looking for the description of the second movie. Okay, so we get the second movie, the Sharknado series, we get the graph it's described in, and then we get the description of that movie. So then we could say, let's delete the old description and let's insert a new description, best of the series. Okay. So the solutions for the where clause are generated first, then we apply the delete, and then we apply the insert. So it's important to note here that the delete won't undo the insert here, because if we insert it before we delete it, then this would match, right? But in fact, we generate the where solutions first. Then based on those where solutions, we delete, and based on the original where solutions, we insert. Okay. So this specifies a deterministic order of operations. So we know what to expect here in terms of the overall results. We'll remove all of the old descriptions for this movie and then insert the new one, best of the series. If we want to work within one particular graph, rather than naming it every time, we can use with. So with essentially says this, like use this default graph. Use this default graph, and every time we don't explicitly mention a graph, assume that this named graph is the one we're referring to. So this query here, when we do the where, we're actually going to do it within this named graph here. And when we do the delete, we're going to also do it within this named graph here. However, when we do the insert, since we explicitly name a different graph, we're going to do it in that graph. We're rather doing it within that graph there. We can also specify if we want a small shortcut. If we write, for example, delete where, it's equivalent to writing delete where the two clauses are the same. So it allows us to delete all matches of the query. It allows us effectively to delete all of the triples that lead to us matching the where clause. So it's essentially it's equivalent to this here, where we have delete with the same pattern as where. Any questions or doubts about that? No doubts. So the overall idea here is we can insert, we can or delete triples from default graph, from different name graphs, whatever we might like. So this is sort of like, you know, inserting or deleting tuples from a table. What about working with the like in the relational analogy, we can create tables and delete tables and so forth. We have a similar language here, which is for deleting graphs or creating new graphs or modifying graphs somehow, like different name graphs. So if we wish to create a new graph, we don't have to create it from scratch. One useful feature is to load. So we can load a graph from the web. And again, this is a nice webby feature where if we wanted to do queries about something in Wikidata, we can just load the graph about, for example, Santiago directly into our database with one command, which would be load. There's this silent keyword, which will essentially throw an error if it's not specified. This means it's optional. It will throw an error if the load fails and this is not specified. But if we put silent, it will just not do anything in the case of an error. And then we specify where we want to load the graph from. So this would be a document online, for example, the Wikidata RDF description of Santiago, which is available. And then we can say into which name graph, optionally into which name graph we want to store it. If we don't specify this, it would be stored into the default graph. So basically, this allows us to pull an RDF document from the web into our local SPARQL store. So this is load. We can use clear, which will allow us to remove all the triples from some name graphs that we specified, or even the default graph. So we can have clear, and again, we can have silent, which will essentially just ignore errors. It will just not do anything in the case of an error. We can specify a named graph to remove all the triples from. We can specify we want to remove all the triples from the default graph. We want to remove them from all named graphs, or we want to remove them from all graphs, which would be all named graphs and the default graph. Okay. So this will fail if the graph does not exist. So if we specify here a named graph, for example, that does not exist, then it will fail. So there is something interesting here, which is what happens to the graph afterwards. Like if we clear all the triples, does that graph still exist? And actually the standard, it allows two different options. It allows for implementations that allow empty graphs. So the graph still somehow exists and can be referenced. But there are other implementations where they don't allow empty graphs, named graphs. So essentially, this means that if you clear a graph, you effectively delete it. So the one difference is with the default graph. There must always be a default graph, even if it's empty. But the difference is in whether or not you can have empty name graphs or not. In some sense, it's a little bit easier to not have to manage empty name graphs. Okay, so what about creating new graphs? We can create a graph. Again, in the case that the implementation allows empty name graphs with create graph, and then an IRI, the name of the graph that we want to create. So this will fail if the graph already exists. So it'll throw an error. Unless silent is specified, it will throw an error if the graph already exists, and existing graphs cannot be affected. So that means that if the graph already exists, it just doesn't do anything. right? It's not going to override it with a blank graph or something like that. We can drop graphs. So this means we actually just completely delete the graph. So we can either delete a specified name graph, we can remove a default graph, we can remove all named graphs, or we can remove all graphs. So again, we have this silent option here. It's important to note that we must have a default graph. So if we drop the default graph, what it does is it creates a new blank one. So there's a new empty default graph. So it's similar to clear. So drop default is the same as clear default here. It doesn't really remove the default graph, it just removes all the triples from it. So this will fail again if a graph does not exist unless silent is specified. We can copy one graph to the other, to another. So here we can specify copy, and then again, the silent option, we specify what we want to copy from, which can be a named graph or a default graph, and to which graph we wish to copy, which again could be the named graph or the default graph. So if the copy fails, we suppress the error. This is a silent keyword that we've seen before. The name of the graph to copy from, name of the graph to copy to, or we can use default if we want to copy from or to the default graph. So this will fail if the source graph does not exist, unless silent is specified. So the destination graph will be created or cleared before the copy is done. So it means that if we already have data and we copy from one graph from graph A to graph B, and B already has data, we're going to delete all of the data, all of the triples in B before we copy A. So A and B will be copies after this in terms of the triples they contain. And the source graph will be unaffected. So we don't, A remains where it is. If we want to get rid of A, if we want to essentially rename a named graph, for example, or move a named graph to a default graph and remove the original named graph, we can use move, which is precisely the same, except for in this case, we're not going to keep the original graph from which we copied the data. So the source graph is dropped after the move, and everything is the same as for copy, as we saw before. What if we want to keep the source graph and we want to keep the target graph and we want to keep all of the data in the target graph? Then we can use add. So in this case, add does the exact same as copy and move, except for it keeps the source graph and it keeps the data that were in the target graph, and it adds to them. It appends to the data in the target graph. So this is the add feature. Okay. Any questions or doubts about? So we have some data to insert or delete triples from named graphs, and we have these features to manage the named graphs in the indexed in the SPARQL dataset. Okay, so if there's no doubts, we have this. You know, you might say, what about OWL? What about Rdfs, right? Here, we're just querying data. We're not considering entailments. You know, if we had an OWL or Rdfs reasoner, it would be really cool because we could query not just over the explicit data that are given, but the data that are entailed from Rdfs and OWL, as we saw in the labs and in the classes. So what about entailments? What about OWL and Rdfs? What's the connection between them? So in SPARQL 1.0, the short answer was that there wasn't really any connection between them. What people would do if they were important to get solutions with entailments would be to materialize or run the reasoning over the graph, produce a materialized kind of extended graph that includes entailments, and index that. So you index the entailments, the materialized entailments, as if they were base data. In SPARQL 1.1, so the materialization approach works kind of okay in certain cases, but it can create a very large graph. And we can have lots of kind of redundant data, like everything is the same as itself, everything is a resource or a thing. You know, these sorts of triples can add a lot of bulk to the data, which we can virtualize. You know, there's tricks. We don't have to explicitly index all of those, but okay. So in SPARQL 1.1, there was explicit support for entailment added. And this is sort of at the kind of cutting edge of the state of the art. So we've seen the new query features and we've seen an update language. In terms of support for Rdfs or OWL entailment, essentially, it states how entailments can be included in SPARQL results. It states the semantics of what it means, what solutions should be returned, given an OWL ontology, for example, or definitions in Rdfs, what results should be returned. So it formally defines what it means to run queries in conjunction with OWL ontologies or Rdfs, which is really nice. So there's support for Rdfs in some languages of OWL. However, it's not very well supported. There are a couple of reasoners, but it's mainly reasoners that support SPARQL. It's not really that SPARQL engines have included support for reasoning in Rdfs and OWL. So there is some support for inference, but it's not super well supported in general. So I'm not going to cover it in detail, but if you're interested, you could check out the book that's online, or you could check out the standard here. Essentially, it just defines what is the meaning, what solutions should I expect if I have an OWL ontology and want entailment. So the last kind of new feature of SPARQL 1.1 are some new output formats, which is kind of, you know, cool, nice for developers, I would say, but maybe not so interesting to talk about. But briefly to mention that for select and ask queries, we can now return data, not just in results, not just in an XML format, but also in JSON or CSV, comma separated values, or tab separated values. Tab separated values, of course, being 100,000 times better than CSV, in my opinion. And then construct and describe, where we have returning RDF data. So in this case, we can return our data in standard syntaxes like RDF XML or Turtle or whatever RDF syntax we like. So the addition of JSON is a nice, or even CSV and TSV, it's a nice feature for web developers in particular, that they can more easily query and process the results. You know, if they're in JSON format, they're using JavaScript, for example, they can more easily use SPARQL as a backend for their web applications, which is nice. Or even not just as a backend, but be able to call, for example, Wikidata to get some results that they need for their application in an interactive way. Last mention is just to mention the protocol, the SPARQL 1.1 protocol. So this essentially, we saw how we could query Wikidata on the web, and we can do this programmatically as well. And in order to enable that, to avoid every different websites defining different protocols or different parameter names like query or queue equals or question or whatever, it standardizes how to issue queries and update over HTTP, given the base URL of the endpoint, how you can specify queries. So how to use get and post, how to accept output formats that can be requested using content negotiation, what response codes should be returned in case of success, in case there's a problem with the actual request, in case the request looks okay, but the server failed to answer because of the query was too expensive, or there was too high load, or whatever it might be. So this is really cool because it means that you can now create clients for SPARQL endpoints, like in JavaScript or PHP or in Java or whatever, where that client can actually implement this logic and can, you know, request output formats in different syntaxes, know how to use get post, know how to handle different response codes, because it's all standardized. So this is an important element of the SPARQL standard, but this is essentially the idea, to standardize the HTTP interaction with the SPARQL endpoint. And this gives us SPARQL endpoints on the web that we can program against. So we can just pick whatever SPARQL endpoint we have that has data interesting for us, and we can, through a client, programmatically, we can query it, get results back, and include those results in our application. And there's quite a lot of applications using, for example, Wikidata to enrich results, or to find more information about the movies it's showing, or to show a map with the places that it involves, which is pretty cool. So this is the query we saw in the first class, actually, about Nobel laureates who have won wars, who have won Nobel Prizes and fought in wars. Okay, so that's the end of the SPARQL section. more or less very similar in certain aspects to SQL, but has some interesting features like property paths for querying paths and graphs, something different to SQL, and also webby features like this federation stuff, as well as a well-defined protocol for having queries on the web. Any questions or doubts? If not, in the class on Wednesday, we're going to have the SPARQL 1.1 lab. Rather than work with RDF Playground, we're going to do queries directly over Wikidata. So we're going to have some queries that you can do in some real data, which hopefully you'll find interesting. Okay, if there's no questions or doubts, then we'll see you on Wednesday in Discord.